Now we are going to discuss about surface tension. Surface tension is basically defined as the tensile force acting on the free surface of liquid which is contact with air, or tensile force acting on the surface between unmixable liquids, right? Between unmixable liquids, right? Surface tension is basically the tensile force per unit length, tensile force per unit length of surface of liquid. Therefore the units of the surface tension is Newton per meter. Units of the surface tension, Newton per meter. Surface tension will be displayed, that the surface tension is presented by the symbol that is sigma. This is the sigma. Right here, this is the one container. This is filled with liquid. So this is the middle. This is within the liquid. This molecular is within the liquid. Therefore, the resultant forces acting on this element or molecular is 0. Resultant forces is equal to 0. Whereas this is located at the near the surface of the liquid, free surface of the liquid, so that one force is acting downwards. So here this is not equilibrium position. Resultant force is not equal to 0. Therefore, here the surface tension acting. Surface tension phenomenon with the help of diagram. Right here, let us consider three molecules of water. Three molecules of water, A, B, C. Right? Molecular A is well within the water. Molecular A is well within the water. That means this is not exposed to air. So that the forces acting on this molecular A is equal in all directions. Equal in all directions, surrounded by the fluid. Surrounded by the fluid means here liquid, or this is the surrounded liquid is nothing but water. Therefore, the resultant force acting on the molecular A is equal to 0. The forces are equally in all directions. Therefore, there is no resultant force acting on the molecular A. Whereas in case of molecular B, this is located at the free surface of the liquid. This molecular B, a part of the portion of the molecular B is above the liquid surface, that is in the air, and remaining part is within the liquid. So here the forces acting on the molecular B is not equal in all directions. Therefore, here the downward forces are high as compared with the upward forces on molecular B. Therefore, on molecular B the forces are unbalanced. But the force on molecular B, the forces acting is vertically downward direction. Therefore, resultant force acting on the molecular B is vertically downward direction. Now, molecular C, that is also provided at the free surface of the liquid. 50% of the molecular C is in the air. 50% portion of the molecular C is within the water. Therefore, the forces acting on the molecular C is also not equal in all directions. But this is unbalanced force. Therefore, the resultant force on the molecular C is vertically downward direction. Right? Therefore, it is concluded that all molecules of water located at the free surface will feel a resultant downward force. All molecules at the free surface will feel a resultant downward force because of the surface tension. Right? Hence, the free surface of water will act like a thin film under tension. Right? Hence, the free surface of water will act like a thin film under tension, right? This is about surface tension, right? Now we are going to discuss about surface tension on liquid droplet, surface tension on soap bubble, and surface tension on liquid jet. Three conditions we have. So what is the surface tension on the liquid droplet? First we are going to express or derive the formula for the surface tension on the liquid droplet here. Now this is one liquid droplet, the diameter of the liquid droplet is small d. Okay, what is happening? This is the liquid droplet. The outside portion is exposed to air. Okay, the inside entire area is filled with water. Outside portion is exposed to air, that is contact with another liquid, but inside portion is completely filled with liquid, right? This is the liquid droplet. Now let us consider one liquid droplet of diameter d. Liquid droplet entire surface will be under the influence of tensile force. Liquid droplet entire surface will be under influence of tensile force due to surface tension, right? Now we are going to determine what is the tensile force. Tensile force is equal to stress into area, right? Now we are going to determine the tensile force. Any force equal to stress into area, that is the standard formula. Now here the tensile force is acting on the circumference or outer side of the water droplet here. Therefore tensile force is acting this entire surface, that is the circumference of the water droplet. Therefore tensile force equal to surface tension stress, that is sigma into pi d. D is the diameter of the water droplet, pi d is the circumference of the droplet. Therefore this is the tensile force. Now the tensile force due to surface tension is equal to sigma into pi d, right? Next one, what is the another force? Force due to pressure inside the droplet. Inside that entire area is filled with liquid, so because of this one we have one pressure, that is the force due to pressure inside the droplet. Therefore force due to pressure inside the droplet, that is equal to pressure force is equal to here also stress into area or pressure intensity into area. Intensity of pressure into area, that is equal to intensity of pressure is P into area. The diameter of the droplet is small d, therefore area is equal to pi d square by 4. This is the pressure force inside the water droplet. Already we have derived surface tension force, that is acting entire surface of the liquid droplet. The pressure intensity inside the droplet is basically the difference between the inside pressure and outside pressure of the liquid droplet, right? Therefore here equating the tensile force to the pressure force. Already we have derived tensile force. Tensile force is equal to sigma into pi d is the tensile force, and pressure force is equal to intensity of pressure into area pi d square by 4. Now d square cancel, pi cancel, therefore sigma P equal to 4 sigma divided by d. This is the pressure, intensity of pressure, or pressure is equal to 4 sigma by d in case of water droplet. Expression for surface tension and pressure intensity inside the hollow bubble. Surface tension, the relation between the surface tension and pressure intensity in case of hollow bubble. Hollow bubble or soap bubble, this is having inside, this is like the diameter of the soap bubble is diameter is d. In case of soap bubble, the outer face is contact with the air, and inner surface also contact with air, because this is the soap bubble or the water bubble. Here, in case of soap bubble or water bubble, the surface tension is acting inner side and outer side, therefore the surface tension force is applied here, that is 2 times. Already I have explained surface tension force is equal to surface tension into pi d. This is surface tension force, but in case of soap bubble, the surface tension force is acting on both sides, inner side and outer side, therefore this is 2 times. Surface tension force is 2 times, 2 into sigma into pi d. And another one, pressure force. Pressure force is equal to, what is the pressure force? Pressure intensity into area, that is equal, pressure intensity is denoted by small p into area pi d square by 4. The diameter of the soap bubble is equal to small d, right? This is the pressure force. Now, if the soap bubble is in equilibrium, the pressure force must be equal to the surface tension force. Therefore, these two forces are equal to sigma into pi d is equal to intensity of pressure into pi d square by 4. Now, d square cancel, pi gets cancelled, therefore pressure intensity is equal to 8 sigma by d. This is the pressure, intensity of pressure of the soap bubble is equal to 8 sigma by 2. Here, in case of water droplet, pressure intensity is equal to 4 sigma by d. In case of soap bubble, the pressure intensity is equal to 8 sigma by d. Right? These two relations are very, very important where we are going to solve the problems. Surface tension on liquid jet. Here, this is the liquid jet of length L, and diameter of the liquid jet is small d, length of the liquid jet is L. Here also, we are going to determine the surface tension force and also pressure force. Surface tension force, earlier case we have taken surface tension into circumference, that is equal to pi d. Here this is the liquid jet, the surface tension is acting on this length of this is equal to L. This is the surface tension force acting on the liquid jet. Therefore, first we are going to determine the surface tension force. Surface tension force is equal to surface tension into, here we are going to take, earlier case we have taken pi d, here we are going to take L into 2 times, that is equal to 2L is the surface tension force. Sigma into 2L is the surface tension force in case of liquid jet. Then another force is pressure force. Pressure force equal to intensity of pressure into, here this is the liquid jet, the length of the liquid jet is L and diameter is equal to d. Therefore, here the area is equal to length into diameter is the area. Therefore, this is the pressure force P into L into D. Right? Pressure force is equal to intensity of pressure into length of the liquid droplet into diameter of the liquid droplet. This is the pressure force. Surface tension force is equal to sigma surface tension into 2 times length. Therefore, equating these two, now we get the pressure intensity. Right? Therefore, sigma into 2L is equal to, right, sigma into 2L, that is the surface tension force, is equal to pressure intensity P into L into D. Now, L gets cancelled, therefore pressure intensity P equal to 2 sigma divided by D. This is the pressure intensity in case of liquid jet. P is equal to 2 sigma divided by D. These are the some of the fluid properties. Here, ideal fluid, already I have explained about ideal fluid. Ideal fluid is nothing but fluid which is incompressible and no viscosity. And the density, there is no change, that is the constant. Because incompressible, there is no viscosity. Density is equal to mass by volume. There is no change in volume because this is incompressible fluid. Therefore, density is equal to constant and there is no viscosity. And another one, real fluid. Real fluid having viscosity and incompressible. Therefore, density varies because density is equal to mass by volume. In case of real fluid, volume changes, automatically density changes. And this is the viscous fluid, non-zero, viscosity having, right? And another one is the Newton fluid. Newton fluid means the shear stress is directly proportional to rate of shear strain or velocity gradient. That equation already I have derived in the last class. Shear stress is directly proportional to velocity gradient or rate of shear strain. And the density that may constant in some cases and also variable in some cases. If the fluid is incompressible, there is no change, that is constant. If the fluid is compressible, in that case that there is a change in the density. And another one, non-Newton fluid, here also the density changes. Some cases that density is constant and some cases that density is varies with respect to the type of fluid. But shear stress is not directly proportional to the velocity gradient. Right? Now, incompressible fluid, there is no change in density, that is equal to constant. Viscosity is equal to 0. That means mass by volume, there is no change, automatical density is also no change. In case of compressible fluid, volume changes, density also varies, and these fluids also having viscosity. Right, last one, ideal plastic fluid. Ideal plastic fluid is also like Newton fluid, but here in case of ideal plastic fluid, the shear stress is directly proportional to velocity gradient or shear strain, but the shear stress is more than the yield value. The shear stress is more than the yield value, that is known as ideal plastic fluid. Here, this is ideal plastic fluid in the horizontal direction, velocity gradient du by dy, in vertical y-axis shear stress. This is the ideal plastic fluid, this is the ideal fluid. So here non-Newton fluid, the shear stress is not directly proportional to the velocity gradient. Here the shear stress is directly proportional to the velocity gradient. This is known as Newton fluid. Right? This is about types of fluids having their properties. Bulk modulus is the measure which is used to which gives the information about the compressibility of that substance. High compressible fluids gives the less bulk modulus. Otherwise, less bulk modulus fluids gives the high compressibility. Right? Similarly, if a substance is less compressible, it indicates that substance will have high bulk modulus. Right? Here some materials given, bulk moduluses of different materials. Aluminum, that is 72 bulk modulus, that is equal to gigapascals. Right, 10 power 9 gigapascals. And brass, copper, glass, iron and nickel, steel. Among all these heads, the less bulk modulus is glass. So it indicates that compared with all other materials, the less bulk modulus gets the glass. Therefore compressibility is more compressibility in case of glass as compared with the other materials. Here these are the liquids having 2.2 gigapascals. Ethanol, carbon disulfate, glycerin, mercury having 25 bulk modulus, water having 2.2 bulk modulus. Therefore the compressibility is bulk modulus is less, automatically compressibility is high in case of liquids, that is the water as compared with the mercury. Right? In gases, the bulk modulus is very less, that is 1.0 into 10 power minus 4. Automatically these are having high compressible fluids. Right? Let us consider that initial volume of gas inside the cylinder is V and pressure is P. Right now here, this is one item, the volume is V and pressure over this substance is P. If the same box here, applied some pressure, that is delta P, in all directions, automatically the volume is reduces. This is the original volume. By applying the additional pressure, the volume is reduces like this. Therefore, the volume of the initial volume of the substance is V, the initial pressure of the substance is P. After applying the pressure, the volume reduces V minus delta V. This is the reduced volume. Right, after applying the pressure, P plus delta P is the increased pressure. Initial pressure, increased pressure. Right, here increased pressure is equal to delta P, that is the additional pressure applied over the substance, and the change in volume is equal to delta V minus delta V, indicates that the volume of the, after applying the pressure, the volume of the substance is reduces. Therefore, the volume is taken as the reduced volume, or change in volume is taken as negative value. Finally, volumetric strain is equal to change in volume by original volume. What is the change in volume? This is equal to minus delta V divided by original volume is V. We want to determine the bulk modulus. For that, we have determined the volumetric strain. Volumetric strain is equal to minus delta V by V. Therefore, bulk modulus is equal to increased pressure divided by volumetric strain. Increased pressure is nothing but delta P. Volumetric strain already we have determined here, minus delta V by V. Finally, the bulk modulus is equal to minus V into delta P by delta V. Right. Now, bulk modulus formula. Bulk modulus K is equal to minus V into delta P by delta V. Here V is the volume, that is in meter cube. K is the bulk modulus, that is in Pascal. Delta P is the increased pressure, that is in Pascal. Delta V is the change in volume, that is in meter cube. Our aim to determine the compressibility. We have determined here bulk modulus. Bulk modulus K is equal to minus V into delta P by delta V. Minus V into delta P by delta, that is the bulk modulus. We want to determine the compressibility. Compressibility is the reciprocal of the bulk modulus. That means compressibility is equal to, mathematically expressed as compressibility is equal to 1 by bulk modulus. Bulk modulus is denoted by K. Therefore, compressibility is equal to 1 by K. This is the formula for the determination of the compressibility. K is nothing but minus V into delta P by delta V. Thank you. Thank you. Thank you, one and all. Right. Now, what is capillarity? Capillarity is defined as the rise or fall of liquid in the glass tube with respect to general level of the liquid in the container. Suppose this is one container, the water is filled in this beaker or container. We are going to install one glass tube. The diameter of the glass tube is very, very small. Automatically the water is raised like this. The rise of water in the glass tube, this is known as capillarity rise. Some cases, if the heavy liquid filled in the beaker are provided in the container, we are going to provide one piezometer like this or one small glass tube like this. The water level in the glass tube is reduces. This is so here we are going to provide one glass tube. Here the water level in the glass tube is reduces. Okay. Capillarity is basically defined as the phenomenon of rise or fall of liquid surface in the small tube with respect to the adjacent general level of the liquid when the tube will be held vertically in the liquid. Suppose this is one container or one beaker. Here the water is filled in this beaker. We are going to install one glass tube vertically. So because of capillary action, the water level in the glass tube increases. This is known as capillarity rise. Some liquids, suppose this is the heavy liquid. This is heavy liquid filled in the glass tube. That is mercury. This is water. Mercury is filled in the glass tube. Here we are going to install one small glass tube vertically. Automatically the water level in the glass tube is below the surrounding level, below the surrounding level of the beaker. This is nothing but capillarity fall. This is nothing but capillarity fall, right? And another one, phenomena of rise of liquid surface in small tube with respect to the adjacent general level of liquid when the tube will be held vertically in the liquid will be termed as capillarity rise. This is the capillarity rise, the water level rises in the glass tube. Here the capillarity fall from the surface level, from the existing level of the liquid in the beaker, that is below this level. This is nothing but capillarity depression or capillarity fall, right? Units of capillarity rise or capillarity fall is mm or centimeters, right? This is about capillarity. Expression for capillarity rise. Let us consider one tank of liquid. This is one tank having liquid like this, water, and tank is filled with water. Let us consider that one glass tube opened at its both ends of diameter small d is held vertically in the liquid as shown in figure. Now this is one container. We are going to take one small glass tube that both ends of the glass tube is opened, that is inserted vertically in the liquid. The water level in the glass tube is raises like this, This is nothing but capillarity rise. This is nothing but capillarity rise. Capillarity rise depends on three parameters. One, diameter of the glass tube, and second one, surface tension, and third one, density of the liquid. Three cases. These 3 points are very important. Capillarity depends on the density of the liquid, diameter of the glass tube, and also surface tension of the liquid, right? This is capillarity rise. And another one, once the glass tube will be held vertically in the water, shape of water in the glass tube will be convex upward. This is convex upward. In order to secure the condition of equilibrium, water will rise in the glass tube above the outside surface level of water. This is the outside surface level of water. This is outside surface level of water. This is the outside surface level of water, but inside surface level is raises like this, right? Now we are going to derive the equation for the capillarity rise. If the glass tube is inserted vertically in the liquid, that is the water, automatically the water level in the glass tube increases as compared with the existing level of the tank. Right now, this is the diagram. This is the water level in the tank. This H is the height of liquid above the water level in the tank. Sigma is the surface tension of liquid. Here we have taken water. If this is mercury, that are different characteristics. This is the water is different characteristics. Now we have taken water in the tank, a glass tube vertically inserted in the liquid or water. The water level raises like this, that is nothing but H. And another one, sigma is the surface tension of the liquid. Sigma is the surface tension of liquid, surface tension of water, because this is the water. And theta is the angle of contact between the glass tube and water. In case of water, the contact angle between the glass tube and water is 0. Angle between the water and glass tube is very less, 0. Theta is equal to 0. Now rho is the mass density of the liquid. This is water, mass density of water. Rho is the mass density of water or density of water. Right, rho is the mass density of water, therefore specific weight W is equal to, here from this diagram, H is the rise of water level. Suppose we have taken one tank, the tank is filled with water, the water is filled up to this level, a glass tube inserted vertically in the liquid or water, the level in the glass tube, the water level in the glass tube increases or raises up to this point. This is nothing but H, and D is the diameter of the glass tube. This is the water. Rho is the density of the liquid or water, sigma is the surface tension of the liquid or water, right? Therefore weight density is equal to rho into g, right? Theta is the contact angle between the glass tube and water, right? Sigma is the surface tension. Now in this case what is happening, the weight of the liquid in the glass tube is equal to force due to surface tension of the liquid at the free surface, right? Weight of the liquid of height h in the glass tube equal to force due to surface tension at the liquid surface in the tube, right? Now for the determination of capillarity raise, the weight of liquid in the glass tube, that is the height h, must be equal to the force due to surface tension at the liquid surface in the tube. Now first we are going to determine what is the weight of liquid stored in the or filled in the glass tube at a height h, right? Now weight of the liquid is equal to mass into volume, weight equal to weight density into volume. Therefore weight is equal to weight density into volume. Volume is nothing but the diameter of the tube is d, that means area into length, that area into h, that is equal to pi d square by 4. This is area into height is h, this is nothing but volume. Volume into weight density is known as weight. Okay, now surface tension force equal to surface tension into area. Here this is the surface tension force into area, that is equal to pi d into cos theta. Theta is the angle between the glass tube and water, right? Now for equilibrium condition, equation 1 must be equal to equation 2. Now therefore that weight density is nothing but rho g into pi d square divided by 4 into h is equal to surface tension force sigma into pi d into cos theta. Now pi gets cancel, square d cancel, therefore h is equal to capillarity raise, h is equal to, right? Now equating these two, this is the weight of the fluid, right? This is weight of the fluid, this is weight of the fluid, this is the surface tension. Equating these two, now rho g into pi d square by 4 into h is equal to sigma into pi d into cos theta. Pi cancel, square d also cancel, therefore h is equal to 4 sigma cos theta divided by rho g d. Okay, this rho g is also nothing but 4 sigma cos theta divided by wd. W is nothing but unit weight, right? This is the formula for the determination of capillarity raise. Capillarity raise h is equal to, so or capillarity raise hr is equal to 4 sigma cos theta divided by rho gd. But here theta is the contact angle between the liquid and glass tube. In case of water, the liquid is water, the contact angle theta is equal to 0. Automatically this cos theta is equal to 1. Therefore h capillarity raise is equal to 4 sigma cos 0 divided by rho g d. But this is equal to cos 0 is equal to 1. Therefore 4 sigma divided by rho GD. This is the formula for the determination of capillarity raise. Capillarity raise H is equal to 4 sigma divided by rho GD, because theta is 0 in case of liquid is taken as water. Now we are going to derive the expression for the capillarity fall. Earlier case, the glass tube is vertically inserted in water, but here the glass tube is inserted in mercury. Right, here same notations what we have used earlier. This is the tank is filled with mercury. This is important term here, mercury is denoted by Hg. Tank is filled with mercury. A small glass tube vertically inserted in the mercury, but the level of liquid in the glass tube is below the surface level of the tank. This is below the surface level of the tank, and this is also convex safe. This depth is nothing but capillarity fall, H. This H is nothing but capillarity fall. Theta is the angle between the liquid, that is the mercury. Theta is the angle between the glass tube and mercury, and sigma is the surface tension of the mercury. And yes, these are the terms used here. Here the liquid is below the existing level of the tank. Therefore in this case, the hydrostatic force, H is the level of liquid in the glass tube, that is the mercury level in the glass tube, that is height of mercury in the glass tube below the level of mercury in the tank. This is the mercury level in the tank. This is the H, that is below the level of tank, that is H. Theta is the contact angle between the glass tube and mercury. Rho is the mass density of the mercury. Therefore W, unit weight, is equal to rho g, that is the specific weight of the mercury. Right? Here there will be two forces acting on the mercury in the glass tube. Force due to surface tension force, acting downward direction. Earlier case, the weight of the water column is equal to the surface tension force if the tank is filled with water. Now here the tank is filled with mercury. Here the hydrostatic force must be, for equilibrium condition, the hydrostatic force must be equal to the force due to surface tension. But the hydrostatic force is acting and the surface tension force equating these two forces. So finally we have the capillarity fall. Right? What is the hydrostatic force? Right, hydrostatic force equal to stress into area. Stress, intensity of pressure, hydrostatic force equal to stress. Stress is nothing but small p into area. Right, what is pressure? Intensity of pressure already I have explained. Intensity of pressure is equal to WH, unit weight of the liquid, into H into area. What is the unit weight? This is the mercury filled in the tank. Therefore unit weight is equal to rho g into H into area. The glass tube diameter is equal to small d. Therefore area is equal to pi d square by 4. This is the hydrostatic force. Hydrostatic force equal to intensity of pressure into area. Intensity of pressure is equal to W into H. W is nothing but unit weight. Unit weight is also nothing but rho into G into H into area is equal to pi d square by 4. This is the hydrostatic force. Then surface tension force. Surface tension force equal to surface tension into pi d into cos theta. This is the surface tension force. For equilibrium condition, hydrostatic force must be equal to the surface tension force. Now hydrostatic force is equal to rho g h into pi d square by 4 is equal to sigma into pi d into cos theta. Now square d pi cancel. Therefore H is equal to 4 sigma cos theta divided by rho g d. Surface tension, that is capillarity fall is equal to 4 sigma cos theta divided by rho g d, where 4 is the numerical value, sigma is the surface tension, cos theta is the angle between the mercury and the glass tube. In case of mercury, the contact angle is taken as 130 degrees. In case of water, the contact angle is taken as 0. Therefore cos 0 is equal to 1. Earlier case, the capillarity raise equal to 4 sigma divided by rho gd, because this is equal to 1. But here theta is not equal to 0. Theta is taken as 130 degrees. Therefore capillarity fall or capillarity depression equal to 4 sigma cos theta by rho gd. D is the diameter of the glass tube. Rho is the density of the mercury. Here the liquid is mercury filled in the tank. Therefore rho is the density of the mercury. G is acceleration due to gravity. Right? Therefore capillarity fall or capillarity depression is equal to 4 sigma cos theta divided by rho g d. Right? This is about capillarity fall. Expression for the capillarity fall. This is approximately taken as 130 degrees. Expression for the capillarity fall and capillarity raise, only one difference. That is, in case of capillarity raise, H is equal to capillarity raise, HR is equal to 4 sigma divided by rho gd cos theta. Theta is equal to 0 degrees. Cos 0 is equal to 1. Therefore 4 sigma divided by rho gd. Whereas in case of capillarity fall, capillarity depression is equal to 4 sigma cos theta divided by rho gd. Here theta is not equal to 0. Theta is taken as 128 degrees or approximately 130 degrees. Right? This is about capillarity raise and capillarity fall. Here one more point. Based on this capillarity raise or capillarity fall expression, the capillarity fall or capillarity raise is directly proportional to the surface tension, and capillarity raise or capillarity fall is inversely proportional to the density of the fluid and diameter of the pipe. Density of the fluid and diameter of the pipe. Right? This is about capillarity fall and capillarity raise.